Yeah, we're good.
Very fun. Okay, so yeah, so if I can share screen
So I think you're
now.
co-host now.
Right. Yeah. And
And would you, as far as questions go, um, are you okay with people just interrupting?
yeah, I
Or
think
would
that's
you
more
like,
fun.
yeah, great.
I'm not saying I can
Um,
handle it well with a math audience, but it should be fun.
yeah, perfect. Are you seeing the chat, or would you like us to
Uh,
let you know if stuff comes up?
I think I
Because we
can.
can do that.
I think I can kind of see the chat. We'll see how it goes if I get distracted by the banner and then move it. But yeah.
I'll try to keep an eye on it. All right. Um, Everything looks good. Are you good to go?
I'm good to go whenever you are.
Awesome. Okay, so welcome back everyone, and welcome Sabrina for our final colloquium this calendar year. We have Sabrina Pasterski from the Perimeter Institute giving us an overview of recent developments in celestial holography from bottom up to top down.
Awesome. Well, thank you very much for inviting me. And also, two reasons why it's awesome. So, the first thing is that I love that it's still like everybody around the world coming together post pandemic for these series. And then, secondly, that it's a mathematical or geometry oriented colloquium because I am very much farther from the math biz side of pep theory. So it's a pleasure to have an audience that can ask me like questions where I should know the answer. I will try to afterwards. So this artwork is fun because basically the Celestial Holography program's kind of developed literally from the bottom up to the top down. So as we're coming from the more kind of terrestrial, like what we see at long distances, trying to understand this full structure of the hologram, especially the collaboration recently has benefited a lot from kind of merging forces with the twisted holography people, where they're finally giving us a top-down construction. So most of this talk, I'll be trying to break out from the bottom up to this picture. And then we'll talk about some fun things that are active directions at the end. Okay, so now the kind of roadmap for what I want to talk about today. I'm going to spend a little bit more time on the soft theorem equals word identity story, which started the program, because I think it distinguishes, or at least sets into kind of context, what the celestial holography program is as compared to other like ways you could look at flat holography. And then along the roadmap, I tried to put a couple places where like the mathematicians might complain at various steps that were, or at least there were insights along the way. And so, for example, kind of like the first, maybe a PDE person might have complaints about what your actual phase space is when it comes to how the radiation is supposed to behave at very early and late retarded times, which we'll draw in the Penrose diagram later. And the thing that underlies the soft theorem equals word identity is antipodal matching condition across spatial infinity. And so that was where like Andy was important. So results from Christodoulou and Kleinerman. And then basically this boost spaces story, we'll try to set it up so you see why we go to this like codimension 2 description of the hologram. And there the particles will be put into a basis where they look like they're 2D conformal correlators. But again, there's now a subtlety about whether you really want to think of those guys as highest weight representations just because they look like they're annihilated by some of the generators, or if there's a subtlety there. And then a lot of the meat of this connection to twisted holography came from really almost like just barreling forward, but assuming that it's a 2D CFT, treating things like you could treat them in a radially quantized 2D CFT, which amounts to various analytic continuations of the like Z and Z bar coordinates of the celestial sphere, which someone who studies amplitudes might call complaints with. But then what you get out of that kind of set of assumptions is a symmetry algebra that makes contact with things that we understand better. And so somehow you're rewarded for being a bit cavalier. And so all of those little places are where a mathematician can come in and fix things or reasonably complain. And so I wanted to highlight that before I proceed with the talk. So the first of the three kind of questions is like, what is celestial holography? And the latter questions will be like why and who, or at least from my point of view for the motivation. But this will be the brunt of the talk. And I would say kind of the motivation for the program is again to look at up at the night sky and like try to apply like what we've learned kind of distilled from either studying black hole evaporation or from string theory, where we have top-down constructions of examples of a holographic duality for, say, ADS spacetime background. And so we then kind of from that believe that there should be a way to have a holographic description of asymptotically flat spacetimes, which would be the regime that's like would capture, say, the standard like scattering processes. And so the kind of key distinction is that we're trying to look at strictly like lambda equals 0 spacetime, and things can be settled in that flat limit. And one of the positive things about that flat limit is that we end up getting a much larger symmetry group. So kind of the first lesson that kicked off this attempt at flat holography is coming from the fact that there's this BMS, Bondi, Vandenberg, Metzer, and Sachs group that's going to be much larger than Poincare. That is the natural asymptotic symmetry group for asymptotically flat spacetime. And that this is much larger than Poincare is where kind of we think like, okay, this can constrain scattering, it might be very useful. And then it's going to lead us down this rabbit hole of this codimension 2 description. But we can always take a step back and just compare it to like the flat limit of ADS-CFT. So I'm going to try to put that into this part of the story too. So when I say ASG here, I'm talking about asymptotic symmetry group. And the kind of story here is coming back from the 1960s, where Vandenberg, Metzer, and Sachs were looking at this like, class of asymptotically flat spacetimes, trying to understand the phase space there and trying to understand how they might like land on just the Poincare group when you're no longer looking at isometries, but you're looking at basically diffeomorphisms that preserve that class of fall-off. And if they didn't want to kill radiation, they ended up with something larger. So that was a pleasant surprise. So let's say give the physicists or like the less mathematical physicist definition of asymptotically flat spacetime. I'm interested in solutions of Einstein's equations with zero cosmological constant, but I want there to be matter. So I'm no longer going to be in Minkowski space, but I'm going to be in something where there's some metric that's non-trivial, that's like sourced by this matter stress field like tensor of our theory. Now I've drawn a doubled Penrose diagram, so some people might already complain about that. But basically what I want to capture is that if you want to look at the, say, initial value problem, like the data for massless fields is going to come in on a surface that is null, called fast null infinity. And then the outgoing radiation is going to be captured by data at future null infinity. And so a lot of the structure of this like enhanced symmetry group is going to be coming from the fact that no, the conformal boundary is null. And so for us, whether or not it's whether we can just kind of co-opt results that were more rigorous from the previous literature, we're basically treating this scribe minus and scribe plus as our Cauchy surfaces for the massless degrees of freedom, and trying to then understand for the symmetries of the S matrix how you can do a symmetry transformation of scribe plus and scribe minus separately and glue them together. So that's going to be the brunt of this like kind of key result from Strominger back in 2013, 2014, was this claim that there's a separate asymptotic symmetry analysis in scribe plus and scribe minus, and the soft theorems verify that you can glue them together. So a little bit more equations behind the words. Basically, Bondi, Vandenberg, Metzer, and Sachs pick a convenient gauge choice where if you're going out to null infinity at a surface that's like fixed u, z, and z bar, so z and z bar are stereographic coordinates for my celestial sphere, then I'm on a null geodesic, and various conventions for so this term here is the area of the sphere, so it's like a luminosity distance. But the important thing for me is that basically the free data is the radiative degrees of freedom are in this ZZ part of the metric, which is sublating compared to the round sphere. And then there's also something that is angle dependent that measures the analog of like the Schwarzschild mass. But now if you had a bunch of boosted Schwarzschilds, it would have an angle dependence. And similarly, this angular momentum aspect. And so essentially what we're doing is they're finding the radial fall-offs consistent with solutions that have radiation. And then in that class of space-times with those fall-offs, you can ask what diffeomorphisms can I do that preserve that class of fall-offs? And they find a much larger symmetry group than just Poincare, because this F now is a super translation. I can translate each direction in the night sky independently as a function of the sphere. And if I don't mind there being punctures in the sphere, I can use a y here, which instead of just the SL2C, like I guess like 1ZZ squared, now I can do any holomorphic transformation. And so those are called super rotations, and then the F's are the super translations. And so if I just look at kind of the mode algebra, I have the Poincare. Yeah. Oh yeah, definitely, yes.
The F's, could you go back a slide, please?
Yeah.
So the F plus is a function of Z and Z bar?
Yes, it's a function of Z and Z bar only, not U. And Y is a function of Z for the standard, for what I'm going to call super rotations. And part of the problem, I would say, with the way that it's set up with this kind of little balancing act here is that one, especially when one tries to take this equivalence between soft theorems and symmetries very seriously, if you have more soft theorems, you might try to accidentally add more symmetry generators. So you could add like directions in your phase space that are pure gauge just so that they're canonically conjugate to some constraint equation that you want. And so there's something very nice about 4D where, because kind of the tails that you expect are at the same order in 1/r as where like your just pure gauge transformation is going to be, you don't miss it. But yeah, I shouldn't have gone through that caveat. But basically, some people might add like basically a Z bar dependence to Y if they were trying to be too general.
Okay, so I just want to understand. So the Y plus is a vector field that's holomorphic. It's a function of Z and not Z bar.
Yes.
And the statement is that if I make a Lie derivative of this metric above, then I just transform the field C and N.
Exactly. So you will transform just C here, and then the angular momentum aspect I think should stay the same. And then basically the C will change. So like the modes of the fall off will change. So you'll map the solution space to itself.
The symmetries we're talking about, can I interpret them as global symmetries of sort of boundary data?
So
at infinity,
you should,
like they're things you wouldn't divide by in a path integral.
Yeah. So we don't want to divide by them. They use the word. So there's various words that I think are troublesome. So we would use the word large gauge transformation to refer to anything which we mean to be asymptotic symmetries, which they act on the boundary. So basically, we don't want to mod out by anything but, I guess, compactly supported diffeomorphisms in some sense. And so I think that if there was a way to make that statement more precise, or like I don't like the fact that the large gauge transformations often people think of as like a topologically non-trivial map from like the boundary to the gauge group, and that's definitely not the case here. But essentially, we're trying to say that the gauge transformations that act at the boundary are in a special class that you should consider compared to the ones that have compact support.
Thanks.
Okay, great. And so then just to look at the,
Hi, sorry. Just one more question. Can you, I haven't followed closely the discussion around super rotations, but they weren't part of the original BMS group.
No, but they were killed at the level of basically they want the sphere to map to itself, right? So like in the same way that like you want like a one-to-one map, you wouldn't be doing that as long as you have poles now. But basically, so again, what's neat about it is that basically the way that Strominger is proving the word identity, you can show that there is the super rotations also are symmetry of scattering, because essentially you're just asking, if I do a transformation of the matter fields in the gravitational field under this Lie derivative and I insert that in my S matrix, do I get that the charge is commute with the S matrix? And the answer is yes. But from the point of view of someone just looking at the metric and saying, well, I really wanted my sphere to map globally to the sphere, why are you doing this infinitesimal transformation? It doesn't make sense. That's why BMS would have killed that. Yeah.
Thank you.
Yeah. So there's that. And then now the BMS group is larger than the Poincare subalgebra, which is this restriction on the modes here. But I want to also point out that, so in the bulk perspective, it seems a little bit gauge dependent in the sense that, okay, first I had to be clever enough to pick a good gauge to talk about my asymptotics, and it gets rid of some like log R's in the expansion as you like kind of recursively solve the modes into the bulk. And then the thing that I'm calling these physical symmetries are like residual symmetries, like residual diffeomorphisms of preserve that gauge fixing that somehow still act on my phase space. And so the way that the gauge choices in there and various like, even like the first kind of proofs of soft theorem resort identity would be using in the amplitudes, harmonic gauge, and in the asymptotic analysis, BMS gauge. And so the things all worked out because essentially if you turn everything in terms of the functions of the free data, then they're going to be equivalent. But it is slightly weird if it seems like the symmetry group is coming from the gauge choice in the bulk. And so a kind of alternative perspective, which is somewhat nice, and also nice to see what's different about the flat limit, is if you just look at the boundary, and I had a time-like boundary like I would have if I was doing ADS CFT, and then I tried to take this Carolian limit, what it amounts to basically stripping off the leading behavior as I take this speed of light at the boundary to 0, gives me as solutions to these basically conformal killing equations in some sense, gives me the BMS action at scry. And so there's a nicer way to phrase it so you're not stripping off the singular part of say this inverted story, because now the metrics degenerate, so you have to be careful with the inverse. In terms of say the degenerate metric at scry and a normal vector which tells you which direction is this U guy. But I want to just point out that you can get the same vector fields strictly from a boundary perspective, which is somewhat cleaner because now it's like not as, it doesn't look as like gauge dependent. And so there's another perspective on flat holography, which will often go by the name Carolian, because Carolian is where the like cone of the conformal boundary is basically squishing up to being just along the time axis. And so the kind of causal structure of null infinity is weird because you have this Euclidean S2 and then a null direction. And so the celestial perspective is basically kind of smearing along that null direction or ignoring anything like that null direction is treated like another parameter in our theory. And we're treating the story as like a 2D CFT. But for some situations, it might be more intuitive to think about the fact that now this boundary is null, and in the null limit, you have kind of enhanced set of conformal symmetries too. So for like kind of the ADS CFT perspective, we want to think of the scattering as being this little tiny causal diamond. And so the causal structure is going to be different. And now we have this null boundary. And on the null boundary, instead of just the global Poincare group, you could see from kind of the contraction I was doing before that the solutions to the conformal killing equations, if I strip off the leading powers, gives me a set of equations that actually have BMS and not just the Poincare symmetry. So that's the boundary perspective. Right. So lesson 1, that would be done. Lesson 1 was that there were an infinite number of symmetries. And from my work, it's more from the point of view of seeing that from the bulk co-opting Bondi, Vandenberg, Wetzer, and Sachs's work, but one could also do it at the boundary. And now lesson 2 is going to be that these are symmetries of the S matrix. And so, and I think this is a nice insight of Strominger, was not just that you can check that those are symmetries, but in order to really prove it, you need to make an assumption that you can simultaneously transform the in and the out state with a diagonal subgroup. Like, so I'm acting the same way with a super translation or super rotation and the future or past, and that those two will be equal, boils down to some sort of antipodal matching of the canonical charge generators near spatial infinity, even though they're kind of infinitely separated in time because of how singular the conformal compactification is. And so what one could say is, okay, so say there's some debate about, do I want to allow myself to do like larger, like say, like, should I have super rotations or should I just have like the global part? Or should I have arbitrary diffeomorphisms of the sphere? Well, one thing one could do is one can check, well, if I assume that I have some action of the symmetry group on my phase space, can I see that my scattering matrix elements are indeed covariant under that? And so in some sense, in the end, you could say that the soft theorem is telling you that you have a ward identity for the symmetry. Or the other way around, you could say the fact that the scattering matrix should be covariant under this symmetries implies the soft theorem, gives you the form of the soft theorem. So that's nice. But let's see how that's done so that we can, I guess, know how you would do it for other examples too. in this BMS story, I had the radiation, then this complex conjugate giving me the two polarizations of the graviton. And then I had a bonding mass and angular momentum aspect term. And the only part that I need to specify is their value at one cut of u, because then my constraint equations, so my equations of motion that end up being to null infinity, because now the normal is a null vector, tell me the u evolution for those two guys. And so in particular, for example, the bonding mass will evolve in time in a way where I can take all the quadratic terms and basically make like a shear inclusive Anik operator. And then I have a part that's going to be linear in the metric. So in this case, the news is the u derivative of the shear here. And the interesting role that that plays is that if I try to look at the commutation relations between that object and my metric, because it's linear in the metric, it's going to shift by a constant. And so that's generating this inhomogeneous like shift of the metric and what Andy would call a Goldstone mode, but lest that be confusing, just that's generating the shift in the metric. And so the way that this equivalence between soft theorems and word identity proceeds is the first thing is that the reason why you think the in and the out should be equal is roughly coming to a statement about the bonding mass, and I guess for the superrotation, the angular momentum aspect across spatial infinity. Now, spatial infinity, when viewed as like I'm approaching it from scry plus versus scry minus, I am basically, because of the order of limits, at infinite past time when I'm coming from the bottom here and infinite future time here. So the fact that they're antipodally related is quite non-trivial. It's kind of the analog would be if I look at the Limit-Beckert solution for a moving point charge, the fact that the point charge started, say, at the South Pole and then moved towards the North Pole if it was moving with constant velocity that way is why kind of in this the simple examples of those just like linearized solutions that you see that antipodal matching. And so I would say that despite maybe antipodal matching maybe also being justified from if you try to lift certain solutions to the Einstein cylinder, it wouldn't have been obvious at the time that Andy was making that claim that it actually should be antipodally matched. I think it was very much looking at like Wiener-Beckert, or also looking at the fact that if I do the transformation, that the shear would shift the same way. So a little bit later, people would look at, say, solutions of the harmonic wave equation in a hyperbolic foliation near spatial infinity, but I still think that that wasn't as robust as this nice surprising result, which is we say they're equal, and then we plug it into a scattering matrix, and then we see it. So the steps to plug it into this S matrix are that basically you're starting with this canonical charge, which is basically the bonding mass now weighted by your super translation, because it's like inserting energy with angle dependence to separately translate different directions of the night sky. And then now you're going to integrate by parts and use the constraint equation to turn this du of mb into a news or shear derivative term and a part that's going to act in the matter fields or the finite energy parts. And so for the super, so I wrote the super translation charge here and then the super rotation charge here, that's my bad. But there's a similar equation for the angular momentum aspect. And when you do this, you get a part that's going to be linear in the metric and a part that's going to be quadratic in the metric, and also to contain the matter field stress tensor. And so those two parts I can now try to evaluate in my scattering.
Could you clarify some terminology? Angular momentum aspect. What is the angular?
So angular momentum aspect is
which is the Bondi news? Is the N for Bondi news?
Yeah, so this angular momentum aspect is another integration constant that you need to specify to fix this du/dz component of the metric at that one order in R. The Bondi mass.
Oh, I see. So it's not visible in this equation. The angular momentum aspect is not visible in this equation, this top equation.
It's right here. This is the angular momentum aspect right here, if you can see.
Oh, it's capital N.
Yeah, capital N.
What's the news?
Sorry, NZZ is the u derivative of this, which also is written by N. So this is good because I take for granted my notation. So definitely call me out on this. So this shear here, if you take a u derivative, we call it the news, and we write NZZ. And the thing where I don't get confused between the two is because there's two indices here and one here. But totally agree that that's not clean notation keeping. So, and so they basically, this is the bonding mass, angular momentum aspect, shear. The shear, if I take a u derivative, will be NZZ is the news, and that's here. Well, if I move my mouse, I also move the slide, so I'm getting confused myself. So basically, this is the u derivative of C now. And then my mistake that I made here was that I wrote down the canonical charge for a different, like the F, the super translations here instead of super rotations here, so that's my bad. But one can imagine that it's basically UMB times DA YA plus NA angular momentum aspect A index. So there's a canonical charge for both the super translations and super rotations. And then I'm just going to integrate by parts using constraint equations like this one to turn it into a soft part and a hard part.
Okay, that's helpful. Thank you.
Yeah, sorry about that. So, okay, good. But definitely call me out on that type of stuff. Okay, so basically now, what am I going to do in practice? All I'm doing is I'm taking the free, like, plane wave expansion for my fields when I'm checking these scattering matrix, like the soft theorem is awarded in me. And I want to strip off what is the actual like shear at infinity. And so this first part here is just basically change of coordinate system. And then I expect from my metric expansion that the metric will go like R, C, like the shear term is order R versus the round term metric is order R squared. So this is 1 over R out front. And I'm taking this large R limit of this integral over my on-shell null momenta. But in the coordinates where I'm basically going out to null infinity, I have this kind of fun separation where I have, because T is now U plus R, what I basically see is that I have a part where it's a plane wave in U, and then this radial part is multiplying something that's 1 minus cosine theta, where theta is the angle between my position in the night sky and the momentum of the massless particle. And so intuitively, it would make sense that if I am sitting very far away from a like source of light, that the light that's hitting me has a momentum that's pointing in my direction if it made it to me. But then effectively the argument is that this kind of saddle point approximation, but large rapidly oscillation in R, as long as omega q isn't set to 0 before you take R to infinity, is going to basically localize or that angular integral so that I am at the same point in the night sky as I'm in momentum space. And so for the massless scattering in these word identities, I end up just leaving a Fourier transform in the U direction, trading my energy for the position I am on null infinity. But otherwise, I am basically relating my momentum space momentum and the direction of the night sky where my operator is sitting because of this so-called saddle point approximation, which again, happy for people to be like, should you be doing that? In particular, one thing one could be careful with is that there's a like a strictly zero energy term that could appear there, but it won't affect the soft theorem. But yeah, so this is the manipulation that they're doing. And now we have the shear, and we're going to plug that shear into an expression where we're saying Q soft equals Q hard, like on this slide. And so now, because I know what the shear is in terms of these A's and A daggers, when I'm acting on an out state or an in state, I basically replace this with the appropriate mode of the graviton here. And then similarly, I know how the stress tensor will like act as a lead derivative on my finite energy field. And so that's one statement of how I know I'm going to plug things into my S matrix. But then when I want to actually evaluate them, I have another tool at my disposal, which are the soft theorems that were studied by Weinberg and then augmented by Cacciazzo and Strominger, because I guess inspired by the fact that for the super translations it was working, so they looked for a subletting soft theorem. And so the claim, just from a momentum space amplitude point of view, is that because when I look at my Feynman diagrams and I have a extra soft particle that's just attaching to the rest of the diagram, I'm only going to get a term that's singular in 1 over omega when I basically attach to an external leg outside of any of the other loops, because this guy's on shell, this guy's on shell, and then the momentum here is going to be like 1 over, say this is P dot Q. So it's going to have a pole in the energy and also a pole kind of in a collinear limit when this guy is massless. And that term is kind of intuitively the leading term that contributes to the leading soft theorem. And then they have an argument to show that the subletting order there's also a universal result. And so the soft theorem is telling me that the amplitude with an extra soft gauge boson is proportional to the amplitude with 1 less soft gauge boson with some either prefactor in the case of the leading soft theorem or differential operator acting on that amplitude. And so this is derived just from the Feynman diagrammatics, independent of any sort of interpretation in terms of symmetry. But what we're going to see is this is exactly the statement that there's awarded in it, because this is Q soft is adding another soft particle And because of this antipodal matching of the bonding mass and the angular momentum aspect, Q soft equals Q hard. And Q hard was just like measuring the energy depositions at different directions of the night sky for these in and out states. And so mechanically, this is how the soft theorem equals word identity is proven. You're putting the charges in terms of, say, bonding mass or angular momentum aspect at spatial infinity. Because of antipodal matching, you assume that the values at the past limit of future null infinity and the future limit of past null infinity are equal. You integrate by parts and turn it into some fluxes. You can substitute for the linearized part, which is the soft charge, just the soft theorem. But we know that the form of the soft theorem actually also matches how the stress tensor, say like the shear inclusive Banach operator or the UZ component analog, act on the in and out states. And so from this perspective, you can see that the soft theorem is basically telling me that the radiation that's very low energy that is basically sourced, is some Green's function for the energy that's been deposited at different points in the night sky. And put another way around, you could say, well, like the soft physics being universal is telling you that there is a word identity. And so this, depending on which way you want to interpret it, you can either say, let's look at soft physics and confirm that there are these symmetries of scattering. Or you can say, because I expect these symmetries of scattering, I just see that the form of the soft theorem is just this Green's function designed so that like some number of derivatives if I integrated by parts here hitting the soft operator would be precisely sourced by all of the matter that was coming into and leaving my space-time at null infinity. And there's some subtleties about also including the caps that like for massive particles, but they can be like put in and it doesn't affect this word identity. So this was the main result that say 2013 to 2014. And then after that, it was like doing a lot of different iterations, trying to interpret the soft charges as various gravitational observables called memory effects. And then trying to push these word identities super far and saying like they'd have implications for like black holes or whatnot. But I don't need to go that way. I just need to basically go to the following statement, which is the first equality is what we talked about, that there's a soft theorem that we can interpret as a word identity because we see this charge coming, the S matrix is exactly the soft theorem once I split it into soft and hard parts. That's telling me the asymptotic symmetry is physical. But on top of that, it looked like certain word identities in 4D could be recast as word identities in 2D. So the subleading soft theorem gives you a candidate 2D stress tensor, which looks like kind of some sort of shadow transformation, something non-locally defined in terms of the soft radiation, but is precisely defined so that it obeys the conservation law I would expect for a 2D stress tensor. And the same thing can be said for, say, like large U1 or non-abelian gauge transformations. Basically, a lot of these asymptotic symmetries for a certain kind of choice of modes look like 2D symmetries. Now, the intuition would be the following. I'm looking at the soft limit of scattering. And so because I'm looking at soft, I'm looking at things that are basically very much smeared along null infinity. And so in some sense, I go codimension 2 by nature of first my kind of data for scattering is codimension 1 standard hologram, and then I'm in the soft sector. And so it's almost like just the zero modes there. And so you might think that, okay, for the soft physics, it makes sense that I have this 2D CFT-like description that I can really play around with because I have Lorentz invariance in the bulk. I have a 2D CFT, and I have super rotations, which are taking Lorentz up to Virasoro. So sure, that's great. But surprisingly, if you really treat it like a 2D CFT, you get more mileage than maybe you would expect. And that's going to be the story of the kind of the celestial hologram and the recent stuff people have been doing. So the conclusion for the takeaway from that last part, which I think is the more kind of fleshing out the kind of raison d'etre for the celestial program, which is coming from the how can we use the symmetries that we expect in the flat hologram that we don't necessarily see in the non-flat hologram, you're going to this 2D description. So celestial conjecture, I guess like going to like the title of this program, is that we can encode the scattering in asymptotically flat spacetimes in terms of a dual CFT living in the celestial sphere. And so basically now the rest of the talk is going to be trying to motivate why this 2D description is natural. And most of it will be based on the symmetries kind of story that we started with. And so in this claim, you have this 4D amplitude being equated to a 2D correlation function. And there's a more naive way of just basically saying, well, what am I doing? I'm doing some sort of integral transform that's changing me from a boost, from a momentum space basis to one where I've basically diagonalized the boost collinear to the massless particles. And so in some sense, it's just an integral transform of the same S matrix that I'm used to. And then one has to motivate, well, why is it useful to do this extra integral when I already have S matrix elements? When am I going to compute that I could only compute in this basis first when I could have just taken my book, whether it's Elving or I guess like other amplitudes results, and then do this integral transform to tell you this. But just at a level of kinematics, because I have Lorentz invariance, I expect these transformed S matrix elements to look like 2D correlation functions. And so that's just a choice of basis, and it works for both massive and massless. Yeah.
So, can I ask a question about that? Could you go back to slide?
Absolutely.
Please?
Yes.
So yeah, I guess you're going to tell us much more about this, but
yeah,
you said we expect the left-hand side to be like correlation functions, and this would be in a local field theory, right?
So we're going to have fun because the 2-point functions. Sorry, I'm not going to say that I answered it any better than I did when I messed it up when I was years ago. But now what I would appreciate is that I would say these are principal series reps that are distributional. So they accidentally look like their highest weight. But for example, the 2-point functions, if I just did this naive thing, would be like P1, like delta function of P1 minus P2. And so it's a contact term 2-point function. So it technically obeys the same word identities for a 2-point function for a 2D CFT. But that singular nature is basically making it look like it's a highest weight state, even though if I smeared along the directions of the night sky, it would be more formally a principal series representation that I would pick up. Sorry,
okay,
I think I'm preempting your question. But
well, I think my question was actually going in a slightly different way.
Okay, yeah.
A different direction. So supposing we look at 3 and 4 and 5-point functions.
Yeah.
And then I ask, as a function of the zi's.
Yeah.
Assume that this function is generically that this integral exists, and so this thing is a function of these zi's as long as the zi's don't collide, and is a single valued function of zi's. And now my question is going to be, is this only non-singular when pairs of zi's collide? Or are there going to be other funny singularities when the Z1 through Zn are in some funny configurations, but no two Z's are colliding? Is there still a singularity? Can there be a singularity in situations where the Zi's don't collide? That's my question.
Yeah, so I want to say first that there's a singularity structure that's weird, which isn't quite the same one because it's like it's the analytic structure of the low point amplitudes. And so, for example, the 2-point function, instead of just having a pole as a delta function, same thing with 3-point functions only have collinear support, and you have to go to a different signature to see a non-trivial 3-point function. And then 4-point functions have a delta function singularity that restricts the 2-to-2 scattering to be in a plane. But that's a little bit different because that's also, say for massive scattering, go to massive and kind of avoid at least the 2-point issue because of an accident with the shadow transform, and the 4-point issue at least. But that's a separate question than the question of now, like, do I accidentally or see singularities that I shouldn't expect? And I think that basically different factorization channels, naively, one wouldn't be able to argue just from what I'm saying here that I wouldn't expect other singularities. And so like Prahar, for example, would point that as a problem with the this kind of celestial 2D interpretation. But I do want to point out that from the point of view of just looking at the out state, and seeing that these operators should be operators that are smeared along light-like directions along future null infinity, I don't think that I would expect anything weirder than if I could perform an operator product expansion of operators on a light sheet or as I approach a light sheet, then because the 4D operator product expansion should make sense, I would think that this one would also. But I agree that I don't have any good argument that when there's some factorization channel that I don't expect some other singularities at other points to appear. I would probably not expect them to be on the real celestial sphere, but I think that's a very good question. And I think the thing is that it would be a sickness for the 2D description, but from my 4D kind of intuition, I would say that at least if I'm only looking at the outstates, I don't see where I would expect anything that would look like it's non-local on the sphere. But
okay, I'm surprised by that answer because previously when I've asked similar questions, people have told me that in examples you could have strange singularities. And this point, this is something I've never understood about the program. If the left-hand side is going to be a correlation function in a local quantum field theory, then it's very strange to have singularities when no two Z's.
Yeah, so what
So
I'm saying is that I think
are there examples where you can actually check if the 4-point function behaves like a local field
so. I
theory?
would say that I've heard the same things you said, where people like, and probably I would expect generally for the S matrix amplitudes that I will have singularities in funny places if I choose the right kinematics. So that basically now there's another like on shell particle. But I think I still want to stand by that. I think if I looked only at outgoing particles where I wouldn't really have like scattering in some sense, that those correlation functions at scribe plus, for example, should behave, because it's like a local theory, then restricting operators to a light sheet. I don't think I have the types of singularities that like my colleagues would see just from the transformed amplitude. So
Okay, thank you.
yeah, but I agree that I don't have an argument for that either. I'm just saying, like, I don't think that like the I think I've looked at the outstate correlation functions. I have basically, I could even go to a position space basis and just talk about OPEs for all these operators being near a light sheet. And I don't think I would have like a kind of locality issue when that bulk is perturbative near scribe plus. But if you have a problem with that picture, then I'm happy to like work backwards and see, because yeah, I agree with you that it would be, yeah. Yeah. So basically it's a very good point, is that the thing about celestial CFT is kind of twofold. Is the one thing is that I have basically this 3D CFT that's in a null surface that I've dimensionally reduced because of some statement about this interpretation of the symmetries that I wanted to exploit. But I also have the matching of in and out. And because of that matching, I basically have particles that can scatter from the past to future null infinity. And it's weird to be gluing two null CFTs together in a way where it's like all of the data is like antipodally matched, where I'm trying to stitch them together at spatial infinity. And so I would somehow think that there is some nice 3D CFT living at scribe plus that should be very similar to like this contraction of the 3D CFT living on the boundary of the ADS CFT story. And that the funny business of treating it like a 2D CFT correlation function could only come from two things. One would be if the integrals along U to define the celestial smeared operators wouldn't converge, and the other would come from the fact that I have in and out operators now, and the causalities work, because all of the out operators commute with each other, but the into out ones don't. So so I can do this transform on the massive guys or the massless guys. And so for the massless one, this intuition for the operators, if they're basically at different points in the night sky, they're space like separated, is fine. But one should be careful with the massive guys, some of the intuition. I'm not sure, I haven't thought about as much for some of the arguments I was just saying. Another thing that's funny is that because I have this U direction, this change to a boost basis is really a change of basis. And so I need another continuous parameter for my field. And so naively, I'm laying these principal series representations, but then the momentum operator is going to basically look like it's shifting the delta. And so the way that we handle it is by treating the conformal dimension as if it's complexified, and then look at where there are poles in the complex delta. So for example, if I did a Taylor series expansion of my amplitude at small energies, then the coefficients of that turn into poles and delta. And those poles and delta are going to be the thing that become now the kind of soft operators, tower of soft operators. They're going to have an interesting collinear limit algebra. But kind of going back to these subtle questions about, if I just transform the amplitude and then try to interpret it like a 2D CFT and I run into some sort of sicknesses, why am I doing it? Well, I would say that one motivation of things, why things should end up working out fine, is because in the bulk, if I'm always dealing with the perturbative CFT in the bulk, and I'm basically like, I should be seeing some of like the I guess just the scalar mean field theory or whatever in 4D restricted to a light sheet that I'm now interpreting as future null infinity. And then the conformal dimension is just the dimensional reduction or smearing of how I'm interpreting that time coordinate in terms of now a conformal dimension to make it a boost basis. So that my soft gravitons coupled to it, I basically am in this BMS multiplet as opposed to just a Poincare multiplet. And then this power of R up front here, that for the scalar case would just be power R, is related to the bulk scaling dimension of the field. And so getting rid of this smearing over the U or V coordinate, this is like the standard extrapolate dictionary I would have in ADS CFT, where the conformal dimension of the bulk field is telling me how much I should strip off when I go out to the boundary with power of the radial coordinate. And so the extra thing that I'm doing is the smearing along the time direction or the null time direction. And again, the motivation for doing that would be because of the way that the soft gravitons couple to your bulk fields. You would expect that the operators that are in this boost eigenstate would now basically be primaries under the full BMS algebra as opposed to just the Poincare algebra. So if you're just looking at Poincare covariance, it might not mean too much to you to want to like go to a boost basis. But the statement would be, I guess, that like, because you're also a Virasoro primary, this boost basis is kind of letting you organize things in terms of the larger symmetry multiplets. But personally, I'm much more agnostic. When I say celestial CFT, I'm happy for it to be a Carolean CFT. I just know that basically when I have the CFT living on the conformal boundary that's null, there's going to be extra symmetries that are come and bite you at some point. And then also, the OPs are going to look weird and the correlation functions look weird precisely because of this degenerate metric on the surface. Okay, so the rough picture that we have is you have this perturbative bulk. I might be computing, say, if I'm only matching to like some tree level or hopefully loop level computations in the bulk, I'm basically looking at correlation functions of local operators in the bulk still. But by going to the boundary, I'm essentially able to like relate those correlation functions directly to these on-shell scattering amplitudes. If I was going to look at the correlation functions just living on, say, future or past null infinity separately, that CFT would be a Carolean CFT. And then when I smear along the null direction, because of this like soft physics inspired symmetry multiplet statement, I land on my celestial CFT. And so now this, I hope, I mean, this might be a bit too glib, but if I wanted to have kind of an intuition for maybe what I would be missing in, say, the papers with Shuhong and what I would expect to get, if I really wanted to say, I'm going to try to replace my computation of my like Feynman diagrams and scattering theory with the operator product expansion that I expect to extract from the collinear limits of scattering, then I would expect more than just single particle operators. I would also want to have an operator for every state in my 4D Hilbert space, which in perturbation theory should be like my Fock space. And so you're roughly trying to make this claim that you can describe the 2D theory as being equivalent to the 4D theory. And so there should be a bunch of 2D operators corresponding to basically boosting the multi-particle states really forward. And so that claim will be hopefully once we get a better handle of how to handle the multi-particle operators too, that you would really be trying to use the collinear limits of scattering to write down your correlation function. And at least very naively, if I just do the same exercise with a free scalar, that's like a formally coupled scalar, so it's a 4D CFT, take the operator product expansion I have there and then try to smear it, you can see like where the subtleties come from the null limit and then smearing. But like I would expect to be able to do this accounting. Now, that's a separate question about the spectrum of the operators that I expect. So I expect principal series for the single particle operators, and then I would expect like taking multiple products of operators in points in the sky, boosting them to the North Pole to give me more states corresponding to the multi-particle operators. But aside from that step, so there was a nice result by Himwich and by Singh, or sorry, I guess Singh is later, but say Himwich, Guevara, Andy, and Pate and friends. What they're doing is just interpreting the collinear splitting functions as an OPE between the single particle operators, which one can do when one's in 2-2 signature. It's completely on shell to be doing this, but it's a little bit subtle to be writing down an OP like this. So they interpret the collinear splitting function because you have an amplitude with 2 particles going collinear replaced with an amplitude with 1 less as something like an OPE. And then when they do this, they find that basically translation invariance is giving you these beta functions, and they have poles exactly the right places so that there's a closure of, say, all of the terms in the soft expansion gave me residues at integer values of the conformal dimension. And now these OPs are closed under that. So first, they're interpreting the splitting function as an OPE. And then on top of that, they're going to now extract these residues. And because so in order to get that for the graviton, they needed to basically look at a holomorphic collinear limit. And what I wanted to point out as a subtlety is that one would expect, like one should be careful about taking, say, if I even had a statement that I have something that's local on the celestial sphere, I definitely should be wary of saying that's going to be local from the point of view of the complexified celestial sphere. So like, for example, if I treat Z and Z bar as independent complex variables, I would expect that the multi-particle operator should give me a different analytic structure. And this was kind of the origin of, it's a little bit out of order with the talk, but there was kind of, it's important that there isn't this kind of confusion in the, there's a claim by the group at Brown that roughly they were looking for the symmetry algebras that I'm going to introduce to the next slide. And then because they were seeing that if I change the effective theories and this different 3-point couplings, that I would no longer have those symmetries, they're trying to make some sort of swampland statement. But the scary thing about it is that they were almost basically saying that the OPE wasn't associative, but that was too fast, because basically the issue was that the contours that they were describing, which involve complexifying Z and Z bar, really shouldn't be expected to be like closed in the amplitudes they have, because basically depending on the theory, you'll have extra kind of branch cuts. And so what I'm trying to advocate in this talk, at least, is that I think from the kind of perturbative bulk version of the story and seeing how you're landing on it from flat space, there shouldn't be an issue with OPE of at least operators in the position space basis at functional infinity, for example. But there have been various claims that have been seemingly interpreted controversially about the celestial description breaking down, and in some sense almost like it's too soon. So I would be fine if the holographic symmetry algebras that I'm going to talk about in the next few slides break down for a lot of instances that we care about, but not that like the trying to use the collinear ellipsis scattering to capture the data of the S matrix. And that's what I want to say. But if we can do various things that if I treat it like a 2D CFT and just to run full force with it, the first thing that I would do is, okay, I have this OPE coming from the collinear limits that tells me how, say, two gravitons, like what graviton coupling from a graviton turns into a third graviton. And there is a kind of universal splitting function for that thing. Now, I also know that that splitting function closes on the residues that I get in the soft limits here. And those values of the conformal dimension would basically be expected to have short multiplets under SL2C. So basically, if I really had an operator that was a standard SL2C primary, and I have a primary descendant for sure, but the funny thing is to say that that primary descendant should be a null state would normally require that the kind of conjugation conditions on the Lorentz generators would be different than the ones that you expect from unitarity in 4D. And so this is not an obvious thing to be doing, but they go with it. And if you go with it, the collinear splitting function is consistent with that truncation, which is good. So now what they're doing is basically they take a single helicity sector, say the positive helicity sector of the gravitons. They've extracted the residues in this expansion in the soft limit. They've then used the fact that those guys have these short SL2C multiplets to write it as a polynomial in Z bar, but each of the modes is a function of Z. And now they're going to treat it like a radially quantized 2D CFT, where those are currents in Z to get a mode algebra. And so these rescaled modes were then identified to be a W infinity symmetry. So it's a loop subalgebra, it's a wedge subalgebra of the loop algebra of W infinity that they're getting from the collinear splitting function of gravity. Sorry, my mouse. Right. And so I think there's a lot of steps there. You should be like, whoa, you should get vertigo from the fact that, first of all, even what Greg was asking about, like there's reasonable issues where you just look at the scattering matrix transformed to the spaces. Does it really look like a 2D CFT? You push it further, and then you're getting the symmetry algebra that you say is like even way bigger than the super rotation, super translations, where you know the asymptotic symmetry interpretation of them. And you're asking, is this somehow still a symmetry? And normally that would be either really interesting because there's a even larger symmetry, or really scary because you're like, wow, like, whoa, you're treating like 2D CFT too much. But the very neat thing about it is that basically this then became a jumping off point where the same symmetry was recognized by people who do, say, twistor theory and twistor holography. And in those contexts, I think there's a more rigorous definition of those modes and why those symmetries are there that I'll get into in my kind of bigger picture motivation for why I like the field of what we're doing. And so even though I'm kind of short of, yeah.
Can I ask a question about this celestial
Yeah.
OPE, gluon OPE?
Yeah.
So can you go to that slide?
Yeah. Sorry.
Yeah. So
This is the graph.
there is no identity on the right hand side, identity operator.
I guess they wouldn't see it. So like, because the collinear splitting function is just the 2 to 1. And so for example, like from the collinear splitting function, you wouldn't even see the multi-particle term. So if you'd have to look at like the Feynman diagrams to try to extract like within like a multi-collinear limit, like what the 2 particle contributions would be to that amplitude. So what I'm saying is that their definitely not writing it down. And I think that they can argue that's the leading like singular term in the Z12 goes to 0 limit. That makes sense.
So there is an identity which is in the dot dot dot. You haven't written it. Right?
So I think there easily could be, I think depending on the helicity, right? So for one versus the other, maybe not, but
the reason is like if you
yeah.
take the inner Brian cat on the left hand side, it's
Yeah.
something non-zero, and on the right hand
I'm
side,
with you,
it looks,
but I would also say one caveat about this OP that they write down, it really is only covariant under half of the Poincare group, because you can even just see like if you do this statement that you're making where I'm going to like sandwich it with another operator, the 3-point function should only have support in 2-2 signature on a delta function of a Z and Z bar, versus the right hand side would now be like a delta function here too. And so a lot of the kind of manipulations you go from higher point to lower point are funny because essentially the completeness relation with like the shadow operator and the operator being the delta function is like flipped. So I'm with you that I assume that, yeah, just from the 2-point function, I expect the identity because there's A's and A daggers with the right helicity. So depending on the ones, but one should be a little bit careful about applying various like standard manipulations to like reduce the higher point to lower point, because the 2-point functions are different. So like where you divide by it is a little bit, but yeah. Good. Okay. Was that enough of answer to your question or scary?
yeah, that's good.
Okay. So in the interest of time is actually perfect because I wanted to kind of raise these questions and then show how now the help from the more mathematically minded people has kind of made this program take off in a way where I'm really like very like honored in some sense. So I think from the way that I was presenting before, I was presenting in a way where it's like, well, would you really expect if you're just taking this tree level splitting function that it goes beyond that? And especially you're looking at, say, only the positively gluons or gravitons going to each other. That seems like it might be a statement only of the self-dual sector. There's various other questions, both like, could I generalize it to when I couple to matter or go beyond the self-dual sector? And then also the manipulations I'm doing, I'm complexifying the celestial sphere, treating it like as a 2D CFT for the holomorphic currents. But why I like celestial is kind of as follows, and it'll close with this incorporation with the twisted holography people. So the first thing, taking a step back, that this program started with was that we're basically looking at various different results from soft theorems and amplitude, the BMS like analysis of the phase space of gravity and the asymptotic symmetry and memory effects. And so that's neat. Started that way. And so because there was this pattern of connections that you could see by connecting those different fields, we had this new sublating self-graviton theorem that was then showing you that there's a super rotation symmetry, a new memory effect, the stress tensor, and then we went to these blue spaces. So we went down a rabbit hole because we saw a pattern that should have been there from the 60s. Look at a new iteration, and here we go. So that's fun. Then what's neat now, and it comes to this questions that we were asking before, is that suddenly by treating it like it's a 2D CFT, there is a claim that there's a much larger symmetry story than you really would maybe want to expect. So when it comes to the soft theorem word identity story, at least there's a pretty good intuition there where whatever matter fields are leaving out at null infinity because there's massless matter, there's some energy deposition that will source the soft modes. And that is an interpretation in terms of like literally taking a lead derivative where I know that I'm staying in my class of metrics in the bulk. So there's a good physical picture for those symmetries really being symmetries. And then it's very satisfying that the soft theorems we know obey them. But go along the timeline and suddenly you're landing at a lot of steps that were assumed to get a larger class of symmetries basically coming from every power in the soft expansion, albeit in this funny collinear limit of scattering, and then also kind of it's a wedge truncation, so it's not quite as large as BMS. Like within the intersection of this W infinity that Annie's getting and BMS would be just half of the Poincare group. So you have this kind of explosion of number of symmetries and kind of a laxer like a reasoning for really them like they should be there in scattering. So how would you go and check it? Well, the fun thing is that people kind of then approach that problem because it's like this bigger claim, like there's so many more symmetries from different ways. So the twister people knew or saw that as basically the nonlinear graviton construction where they know how to get the same W infinity from the way that they would construct the graviton vertex operators. People like Laurent would go from a phase space point of view to try to look at like how I am basically preparing these operators near null infinity, which have the commutation relations equal to the radial commutation ones in this kind of funny complexified 2D celestial sphere. The soft theorem is how it was derived originally, I guess. And then the twisted holography people were identifying those symmetry algebras as their chiral symmetry algebras. And so what's neat about that then is that suddenly you have very particular, especially in the twisted holography story, which I don't know enough to want to say, so I'm trying to just say it's awesome that to be at Perimeter with Kevin, is that now you suddenly have examples of a top-down hologram almost that meet like the criterion of what would be a success for a celestial CFT, is that you propose that there's some symmetries that you're seeing from the infrared, and those symmetries are enough to identify an example where it actually is like a top-down hologram. Now, to be fair, it's a funny gravitational theory. It's like some twister theory of Burn space, and you don't have like standard like Einstein-Hilbert gravity, but it's neat that someone could be more rigorous because they have a more rigorous framework for interpreting the same symmetries that you extracted in a very weird way, collinear limits of scattering for tree level, taking like complexifying the celestial sphere, doing some 2D CFT manipulations that you really shouldn't expect to be able to do from the bulk unitarity, and voila. So that was super cool because suddenly now you have different perspectives, and on that side they might be able to kind of extend like different examples of like a celestial like top-down hologram, versus the bottom up also gives you a large phase space of different things you can screw around with. And so my own research more recently has kind of been on the amplitude side and the covariant phase space side, like what the Ront is doing, to try to connect the kind of observables we're looking at to the conformal collider literature, but that's just me. What I think is kind of exciting also as a rebrand, because we now have this collaboration, is that it's somewhat natural that if I'm just saying I'm looking at flat holography and the whole celestial program is coming from the symmetries you get in the flat limit, that's great, but we know that it should connect to it from qubit. It should connect to scattering amplitudes, and then also like Bootstrap, because I'm trying to phrase the S metrics in terms of collinear limits of scattering, giving me the OPE coefficients. And so what's fun is kind of the thing in the middle there is these hard charges that were appearing in the celestial symmetry story are also like the Anik operators that have certain positivity constraints are useful in quantum info, and they, because they're like their stress tensor, like their correlation functions are also their OPEs more universal, have appeared in the Bootstrap literature. So that's where I'm trying to latch on to what is a fun framework that not only connects a lot of interesting research. And just as a final shout out to some of the people here, if we look at the people in our field and try to look at who's worked with who, you can whittle it down to how we're clustered. And this was a really rough clustering for like before strings. I try to make it a little bit better, like looking at each person has a bibliography of like the bibliography for any paper a person's written can be clustered. And then you see kind of where the formal QFT people are, the scattering people, Bootstrap, ADS-CFT. But for fun, the celestial people really are in at least a bunch of the different disciplines, which is fun. And we have a great team of people as PIs, and an awesome team of people at Perimeter, and a lot of questions to ask. And so that's where I wanted to leave my talk, hopefully not too much over time.
Thanks so much. Yeah, thanks for joining us and and doing this. Any other questions?
Yes, Craig.
Yeah, go ahead, Craig.
No, I had two questions. One was you flashed some machine learning things at the end. What was your data set?
Oh, my data set was just Inspire. So I have
okay, that's all.
So but the fun thing is I do have a side passion project, because you could totally take like, okay, what has Celestial done that's new? And like, let's turn that around and be like, we're connecting different research canons. Can we scale that up with, yeah.
Okay, yeah, I got it. So, and the other question is, you said something really quickly about a non-associativity of OPE. So going back to those correlation or alleged correlation functions, where I stopped you and asked a bunch of questions.
Yeah.
I mean, do we expect it to satisfy the conformal bootstrap in the 4-point?
So what I think is fun is that I think when I give a math biz talk, it's like I know I'm going to a confessional or whatever. It's like I need to tell you, these are all the things that could be wrong with this framework. So please, so that's where I feel bad that I might have like pushed some people under the bus a little bit with like here are the problems that people have run into. But okay, so I would expect that if we phrase the right question, we could do a conformal bootstrap. Now I think that's coming from the intuition of I know it's really not that different from the ADS-CFT thing, but I do see that the difference that comes in is that when I go flat, I have a larger symmetry story. So if I ignored the whole soft physics story that motivated celestial CFT, I really don't think things should go that wrong, just the way that you would extract, say, from correlation functions in ADS CFT, the S matrix. And so for me, that's where I'm confident there should be a nice bootstrappy statement, but I wouldn't put all my chips in saying that it needs to be in the celestial basis, that it's the cleanest. I do think, though, once we understand the richness of like this point, like BMS versus Poincare, that's where the celestial basis is going to come in, because it was the kind of the BMS multiplets that were the reason for going to this boost basis and doing that particular dimensional reduction. So the problem that I was mentioning with these associativity of the OPE was that basically these currents, this W infinity symmetry, was defined in terms of this, assuming this truncation of the Z and Z, like the, say, the Z bar terms in that scattering amplitude. And one can already kind of see that if I look at like multiple collinear limits of scatter, even at tree level, that I would expect a different analytic structure where I should be wary of doing that. And so roughly the contours weren't closing.
Yeah, that's
so,
the comment you made.
Yeah.
And I was wondering if that meant that the 4-point function did not satisfy the conformal bootstrap.
I would think that it would satisfy the bootstrap under the symmetries that it should, which I think should be BMS. I'm not going to swear by the W infinity story for any given flat hologram. Like,
sorry. I mean, the bootstrap equation is not an equation relative to a choice of symmetry. The bootstrap equation is a statement about about this analytic function of 4 variables.
Sure. So what I'm saying is that it should satisfy the bootstrap equation to the same extent of, like, if I want to just look at primaries and their crossing, then it should be fine. I think there could be a breakdown of the decomposition in terms of multiplets of symmetry.
It'll satisfy the bootstrap. I see. I'm starting to understand. So you're saying it'll satisfy the conformal bootstrap for conformal primaries of certain symmetries, but in other words, not for all operators, but for primaries.
I would be. So I think anything that can be phrased in terms of the global symmetry group is going to be fine. And if I had to go to like impact parameter space, so instead of delta, I go with U, I'm fine with doing that. I think that the interpretation in terms of them also being symmetry multiplets. So if the goal is to take, like, basically use these symmetries to all their power and write everything in terms of some primaries under like a larger symmetry group, I'd be very wary of like the W infinity symmetry being the thing that's supposed to organize something that then is self-consistent. But yeah.
Okay, thank you.
Yeah.
Yes, Seb?
Hi, Sabrina. Thanks for the great talk. Just a question about gravity. Does gravity matter? Can you what happened? I mean, can you decouple gravity and just consider celestial holography without gravity?
So I would say that it should matter when you're doing more interesting questions. So for example, it mattered in the statement of the, say, it matters in a couple examples. So for example, it would matter when I want to talk about the ward identities. The ward identity is telling me that somehow I can replace this insertion of Banach operators with insertion of soft gravitons. So if I was just in the matter sector, I might have that there's these operators that are kind of protected, like this, whatever the Banach operator is compared to like coming from the stress tensor has a definite conformal dimension. But I have like a kind of null state that comes out by also having gravity. I also wouldn't have the BMS primary condition if I didn't have the gravitational modes, I think. But a lot of the story, but then I can also look at just the fact that before I worry about then having like Q soft plus Q hard equals 0, I could just have that the Q hards obey the BMS algebra and I would have it just in the matter sector. So there are some things that are true, especially in this case where I'm always looking at kind of perturbative bulks just in the matter sector. Another example would be if I'm just in the wedge subalgebra, I don't have kind of light ray supported operators, but I kind of smear them in another direction, at least one other direction, I think. I'm not sure if it's the full celestial sphere. And I will have like just the matter sector realization of the W infinity story. But if I wanted to try to get light ray supported operators that go beyond the BMS, I would need to have like gravitons, or for the BMS case, I would have collinear gravitons giving me the algebra on phase space that I would expect. So depending on which direction you want to go, you start seeing where you need to add gravity in different ways. But ideally, the whole point of like the fact that it should be this like a hologram should rely on like the fact that I can time evolve using my like Bondi mass, which would need like gravity. So
Thank you.
Well, I have another question.
yeah.
What is the advantage of doing celestial holography rather than just taking the flat space limit of ADS4 CFT3?
Yeah, so I'd say the advantage is in those super translations. And so, okay, so for example, what one might say, okay, so like there's something special about 4D in the sense that we have Virasoro as compared to the Lorentz group, but I think that generically, like a null CFT as opposed to before you take the Crowley limit, will have an analog of like super translation symmetries. So that is something that you shouldn't see, except for, I mean, in the sense that the way that you see it from the flat limit is like, say I look at, say I was just doing my own thing. I have my metric with the speed of light that's going small, but not exactly zero. If I would normally not have to worry about the inverse version of the conformal killing equations. I would just have like one, and because everything's invertible, it's fine. And so if I am strictly solving the system of equations that I get by stripping off the leading singular term in this up index guy and the standard like down index guy, I get BMS. If I solved it order by order, I would go back to getting just Poincare. So I'm saying that there's something funny about how you're defining what survives in the flat limit that lends you an enhanced symmetry algebra. And so it's not clear to me that like that's something I would naturally know how to land on from ADS CFT per se. And the other question is kind of interesting is when you try to look at like how does my metric limits to being flat. So if I have the Pfefferman-Graham expansion, I will have terms that are singular in the cosmological constant in the stress tensor that I would have. So for example, one kind of other, so that's one weird thing. And it's also related to the fact that the metric in ADS that would have radiation when you go flat has an order lambda. So it goes to zero as the cosmological constant goes to zero, correction to the round sphere metric. And so now you have a time-dependent round sphere metric, and one could say, depending on the person. Now, of course, when you put operators, you're backreacting and changing the geometry. But strictly speaking, like the radiative backgrounds now don't have this conformal isometries because like that radiation profile would be breaking it. But that's a term that's suppressed as you go flat.
But
so
isn't
there's
it
a couple
true
weird
that
things that
isn't it true that the scattering amplitude, which is like invariant statement,
Yeah.
the flat space scattering amplitude can be obtained from just taking the flat limit of ADS, and that's the
Sure,
only
so, but
invariant statement you can make.
So I think so. I want to unpack the invariant statement separately. But I think that the reason why it's consistent with what I was saying is because I'm basically taking global ADS, adding some operators, like it's whatever stress tensor insertions, and then I'm effectively backreacting. So like it's not a problem that my boundary conditions are weird when I want to go like the phase space of boundary conditions that I want to include when I want to include radiation in flat is a little different than the boundary conditions I would be used to in a normal ADS CFT. But it probably isn't effectively a problem from the setup in terms of correlation functions. So that's one thing to be wary about in flat. It's not clear that the boundary conditions that you're used to, that you're assuming to make sense in the ADS context are what you would want to assume in the flat limit, right? Like, so for example, having, like looking at a class of metrics where the round sphere metric in ADS now has a time dependence that is basically the news. So that's one thing that can be different about going flat. And then the question about like the S matrix being invariant, I guess because it's a boundary correlated, the same argument about like what observables are well-defined in quantum gravity tethered to the boundary is good, fine. But I do want to point out that like the boundary correlation functions still transform non-trivially under like super translation, super rotation. So like the asymptotic symmetry group will transform them. So they're not quite like large gauge invariant until you take everything into account, at least the individual operators.
Thank you.
Yeah.
Right. Well, we're a bit out of time and should stop for now. But let's thank Sabrina again. And thank you all for coming. And we'll wish you all a good December.
Happy holidays.
Yeah. Yeah, happy holidays. Take care.
Thank you.